Hi guys, Omoras here. Today we're going to see what happens when we force a PCI-Express GPU to run with extremely limited bandwidth. Basically the way PCI cards worked back in the day. We'll be testing some older GPUs, but also a modern one like an RTX 5060 Ti. Usually you can heavily limit the GPU bandwidth by forcing a card to run at PCIe X1 speeds. But this time we're taking further, so we're going to make a GPU behave like a classic PCI card with just 133 megabytes per second of bandwidth. Actually, I suspect we may get double the regular PCI bandwidth, because both bridge chips doing business in this setup are capable of running at 66 MHz. First, we've got the PX8112 handling the PCIe to PCI conversion on the way down, and then the PL7C9X bring it back up to PCI-Express. Now, to see whether this setup can really hit 66 MHz, I brought an NVMe SSD into the mix. The transfer speeds will tell us immediately. And sure enough, hardware info reports that we're running at 66 MHz, and the results in Crystal Disk Mark confirm it. This whole how bad can it get idea didn't come out of nowhere. Right now I'm setting up my multi-boot Ryzen 9 9900X PC, and I've run into a problem. I can't use my RTX card in the first PCIe slot. That means I have to put it into a slot with much lower bandwidth. Why? Because I need to run two discrete GPUs. One is for keeping operating systems like Windows 98 running, while the other handles modern stuff like this RTX 5060 Ti we're checking out today. Not too long ago you could just jump into the BIOS and tell the system which GPU you wanted as the primary display. It was simple and logically useful, but I haven't seen that option since around the Intel 4th Gen motherboards. These days the BIOS gives you choices, just not the ones you actually want. You can pick integrated graphics or whatever card happens to be installed in the first PCIe X16 slot. The good part is that it doesn't care if that card is an NVIDIA 7900GS from 2006 or an RTX 5060 Ti from 2025. The problem is that the operating systems like Windows 98 can only use the primary video adapter reported by the BIOS, and that's hard-coded in the OS. There is really no way around it. And speaking of coding, just a quick shout out to today's awesome sponsor, boot.dev. So if you ever thought about learning to code but got bored halfway through some dry tutorial, boot.dev basically said, well, what if we just made it fun? Here is how it works. The whole experience is designed like an RPG. You level up, earn XP, unlock achievements, take on quest, fight bosses, and if you get stuck, there is Boots, this bear wizard AI tutor who helps you figure out what's going on. So instead of just watching someone else type, you're actually building real projects in languages that companies hire for, like Python, Go, SQL, TypeScript, or Java. And you're not just learning theory, you're writing the kind of code that can land you a six-figure job, maybe even remote. We're talking over 100k while coding from your couch. Well, that's definitely something to think about, especially since all the content is free to read and watch. You only pay if you want the interactive stuff, the hands-on coding, progress tracking, and all the game mechanics. Plus, there is a 30-day money-back guarantee, so if it's not your thing, no stress. So, if you want to give it a shot, just use code OMORES at boot.dev for 25% off your entire first year. Use the link in the description or this big QR code on the screen to start your new journey. Alright, now back to our GPUs. For the first test, let's check out this NVIDIA 7900GS, which is kind of a regular on this channel. I've tested this card so many times already, and on Windows 98 the results are usually around 56k points on this Ryzen 9 system, and close to 62k points on Windows Millennium, which for some reason is even faster than Windows 2K or XP. I still don't really know why. I was honestly afraid that putting the GPU behind two additional PCI to PCI bridges would completely confuse Windows 98, but nope, the card installed just fine on the first try and it actually runs stable. The performance though, well, it's not great. At just under 10,000 points, we're getting about 1/5 what this card normally scores in 3D Mark 2001. And it can get even worse. For example, in Quake II it scores only 53 frames per second, whereas normally it gets close to 1000 FPS at 1024 by 768. But hey, at least we know it works. Next, I tested this NVIDIA GTX 1660 Super. This was a really good card when it launched back in 2019, and in some games it can even get fairly close to an RTX 2060 in raw performance, except there is no hardware ray tracing, of course. Surprisingly, the GTX 1660 Super also works with this PCI-Express to PCI and back to PCI-Express adapter combo. The driver detects the card running at PCIe X1 speed and doesn't really question what's going on, which is interesting because, as you are about to see, the driver also can just refuse to work entirely. This time performance is noticeably better. I tested the card on my Ryzen 9 3900X system because under these conditions using the newer 9900X CPU wouldn't make any real difference. In the no-mod steel benchmark, the crippled card running at PCI speeds shows about 33 performance loss, and it improves a bit if we turn off screen recording. Newer games that rely on the Vulkan API, like the remastered version of Quake II, actually runs very decently. That's because they expect GPUs to have plenty of onboard memory, so they load most textures locally at the start of the level and don't constantly hit the PCIe bus. Older games are a different story, something like Stalker released in 2007, which has a minimum GPU memory requirement of just 128 megabytes. Well, this one does exactly opposite, constantly streaming data over the bus, and the performance absolutely tanks. So we're going from hundreds of FPS when running the card normally, down to about 10 FPS when going through the PCI adapters. Next, I tried the RTX card with the same adapters, and this time things didn't go according to the plan. The system booted normally, but both Windows 10 and 11 refused to initialize the PCI to PCI bridge created by the PX8112 chip, the one that lets you use a PCIe card in a PCI slot. The driver couldn't find any matching hardware IDs, and I couldn't locate the card for a manual install either. And I was worried about Windows 98 getting confused by all those bridges. In any case, the GTX 1660 Super worked well enough to call this no bandwidth experiment a success. So I moved on by installing the RTX card in the PCIe slot with nothing in between. Just like every other 5060 Ti on the market, this card is wired to use only 8 PCIe lanes. So theoretically, we're looking at a max of 32 gigabytes per second on PCIe 5.0 and 16 gigabytes on PCIe 4.0. Now my X670 motherboard, even with a PCIe 5.0 CPU like the Ryzen 9 9900X installed, is supposed to run the main PCIe slot at PCIe 4.0 speeds. However, after the latest BIOS update, this Asus Prime X670 actually reports PCIe 5.0 speeds. That's what the BIOS reports, and it looks like GPU-Z, hardware info, and every hardware info tool are sticking to that story. I'm not so sure since I don't know of any other X670 board that supports PCIe 5.0 outside the M.2 slot. Either way, the 3D Mark results are exactly where you'd expect and slightly above average with some extra boosting. Now here is the interesting part. When I reran Steel Nomad with the card in the bottom slot, the score was actually a tiny bit higher. It was within the margin of error, let's say, but the bottom slot only has 4 PCIe 4.0 lanes, so we're getting just 8 gigabytes per second bandwidth over the PCIe bus. But as we already know, that's not such a big deal, especially for a benchmark like Steel Nomad. So I had to try something heavier like Half-Life 2, the RTX version, which is pretty demanding for any RTX card. So here we have side by side the 5060 Ti running with full bandwidth available, which is 32 gigabytes per second, or just a fraction of it, just 8 gigs. Anyway, in both cases we're getting over 200 FPS at 1080p with deep learning super sampling, or DLSS, on, which, well, I'm sure you know what it is. If we look closely, we do lose some FPS while running with much lower bandwidth, I would say around 5%, but the big difference is in the lows, so we may hit the bottom more often, which kinda makes sense if the card has to wait for its data. Without DLSS at 1080p, we're getting about 100 FPS, but nevertheless, it looks like I'm not losing much by giving up the first PCIe slot to the GeForce 7900GS, so I can have a very beefy Windows 98 setup, where I can also play Half-Life 2, but the original release, of course. Now, in the end, if you're curious how Half-Life 2 looks while running with ancient technology like Windows 98 and DirectX 9 from 2006 and just a 256 megabyte DDR GPU, let me show you the same level we just saw on the RTX version. If we are running it on something like this Ryzen 9, we can hit over 150 FPS in Full HD with everything maxed out. Sure, the RTX version looks better, no question, but honestly, I'm not sure what that really says about how far we've come, or maybe how far we haven't in the last 20 years. That's it for today, guys. Many thanks to boot.dev for sponsoring this video, and don't forget to check them out at boot.dev. And if it helps, I put this huge QR code on the screen. Amores out.